Hi, and welcome to the second lecture of Intro to Modern AI. This lecture is going to be an introduction to supervised machine learning. Supervised machine learning is actually the entire first part of the course. So, in this entire first, I think it's about 7 or 8 lectures, we're going to focus on what supervised learning is, and then in detail, how you implement it, how you implement all the components of a supervised machine learning algorithm, the models, the loss functions, the optimization. And then we're going to focus a lot on neural networks in particular. However, to start with, this lecture is going to capture at a high level the basic supervised machine learning paradigm and the different components and notation involved with supervised machine learning, again, at a fairly informal level before we dive in later lectures to capture this much more formally using the notation of linear algebra. In particular, what we're going to talk about today is 4 things. We're first going to talk about the supervised machine learning paradigm. Specifically, we're going to think about how this differs from traditional programming and fundamentally what makes supervised machine learning different in some sense. The next thing we're going to talk about is some basic notation. Things like inputs, outputs, desired outputs, predicted outputs, training sets, this kind of stuff. And then we'll talk about really a roadmap for the next several lectures of this course, which are going to be the 3 ingredients of a machine learning algorithm. It turns out that every machine learning algorithm, be it simple linear regression or be it boosted decision trees, actually roughly follows the same formula of 3 ingredients. They are going to be the model, the loss function, and optimization, but we'll cover those all today. We'll discuss each of those and how they are important to defining the overall sense of what a machine learning algorithm does. And finally, we'll end talking about generalization. In some sense, the whole point of machine learning is that while we're using data to build these models, we want them to work well beyond the scenarios that we first give to them as data. And so we're going to use the notion of generalization to capture that effect. Okay, so let's jump into first the supervised machine learning paradigm. Now, there are other types of machine learning than what's typically referred to as supervised machine learning paradigm. There are other types of machine learning than what's typically referred to as the supervised machine learning paradigm. But supervised machine learning, at least algorithmically, forms the basis for virtually everything you'll see in modern AI. Some people might call this self-supervised based upon kind of how you get the desired outputs, as we'll call them, into the data set. But really, at an algorithmic level, what most current machine learning is based upon is, in fact, the supervised learning paradigm. So, in order to describe supervised machine learning, I'm going to contrast it with the typical way we write programs, computer programs, that is. And this might seem actually overly pedantic because we don't often honestly think that much, at least when we're first learning programming, about how we go about writing a machine learning or a classical non-machine learning program. But this is important to contrast machine learning with this more classical approach. So let's think about how we solve, for lack of a better word, a usual programming task. Usual programming approach. Basically, what we do is we start off with some specification of the desired behavior of a program. And this could be a formal specification, like you might have if you were if you had some formal spec that had to control some system and embedded device, and you had to formally determine what are the inputs, what are the allowable inputs, allowable outputs. It could be formally specified in terms of the preconditions or postconditions of a function, or it could just be specified somewhat informally, like take this list and sort it, and your input should be a list of elements in any order, and the output should be a sorted list. So we start with some specification of what behavior we want out of the program. We then, for lack of a better description of it, we kind of think about the logic that will achieve that behavior. Right? We think about how could you formally, line by line, in code or in some other formal logic, take an unsorted list and transform it into a sorted list. Now, again, there are different ways to formalize this. We can think about this being somehow much more, um, just much more formal than this would be, this description here. But this is a reasonable description. This is how I program usually, right? I have some problem, and I just think about how I can break it down step by step and solve it. And then what comes out, and then the next step after that is that we write that program. We formalize that logic in some programming language in the form of some program. So I'll write a Python script or something else that actually accomplishes this program. And that's, it's a very high level, extremely informal description, but I think it actually captures roughly what was done with programming. Got the G on programming. So what I want to contrast this with is machine learning approach. Be consistent in my capitalization here. And here, the important part is that when you use machine learning to solve a problem, you don't always have a formal specification of the problem itself. What you have instead is you have examples of the desired behavior. You have examples of inputs your program could see and the desired output that you want your program to produce. It's a very different paradigm of what you have in a program than traditional programming. You start with kind of illustrative examples of how you want things to work. We then feed these examples into a machine learning algorithm. And I need to differentiate now between the algorithm itself and the resulting program it produces, the algorithm is still code that we write, but what the machine learning algorithm produces ultimately is it produces a program that solves that problem. I should say something like a produced program. Move my head to the side here. I am going to put program in quotes there because this kind of program that we produce with the machine learning method is really quite different from the programs we're used to producing when it comes to kind of traditional programming. The programs here are very simple. They're sort of very, very simple mathematical constructs that sort of manipulate the inputs with a whole lot of mathematical operations and produce an output. And it doesn't look like normal code. We aren't talking about using AI to write a program here. We're talking about kind of a simple function that maps from inputs to outputs. Okay, but this, roughly speaking, is the machine learning paradigm. Now, there are some advantages of both approaches here. The usual programming approach, for all its downsides, is actually, in many cases, quite powerful. There are many settings where we really should solve problems, where we really do have a specification of the complete set of desired behaviors we want a program to exhibit. We know exactly how every input should map to every output via some mathematical definition. Again, sorting a list is a good example, right? We know exactly what it means in terms of verifying whether a list is sorted or not, and we have a set of allowable inputs that could go into that program. In those cases, the usual programming approach is genuinely very valid, genuinely very useful. But there are a lot of problems where we just really don't know how to write a program to accomplish this. One of the examples we're going to use a lot in this class is the example of image classification, at least in this first part here. How do you write a program that can take any image as input and output a description of what's in that image? That seems extremely hard. It's much harder than writing a program that can sort lists, right? Think about all the allowable images that you might have as input. This contrasts with the machine learning approach, where for a lot of problems, it is much easier to specify examples of the desired behavior than it is to actually specify the desired behavior itself. It's kind of like saying what you want instead of saying how you want it done. And for these settings, things like image prediction, things also, by the way, like answering arbitrary questions via a chatbot. These are cases where it's much easier to specify what we want in terms of examples, sometimes many examples, than by specifying the exact way a program should solve it. And in those cases, the machine learning approach ends up being by far the best way we know of to solve certain problems. I certainly am much more capable of writing using a machine learning algorithm to produce a program that can classify images than I am at manually writing that program. Okay, so with that as basic background, let me define some rough notation here. And I'm going to define, this is all still going to be fairly informal. As I said, we're going to formalize a lot of these things in the subsequent lectures using the notation of linear algebra. But we want to start with a fairly informal notion of what we give to a machine learning algorithm, and in some sense, what it produces. So the first bit of notation I'm going to define when it comes to machine learning is the notion of an input. And the input is an example that we want to give to our program. So, I mean, I'm sort of using the word to define itself, I know, but in some sense, this is just going to be the input that we will provide to the ML. So this is when we have the resulting program that we produce within a machine learning algorithm. What are the inputs that we want to be able to give to that? There's also the notion of a desired output. They're sometimes also called targets, but I think desired output captures the term better. This is, for a given input, what is the output we want our ML program to produce importantly, for some specified input, or some corresponding input. And finally, we have the notion of a training set. And this is a collection of inputs and the corresponding desired output that we want the ML program to produce. Collection, inputs, and their corresponding desired outputs. Okay, that actually for now is a good description of some of the kind of general notation we'll use. But it doesn't really capture, in my view, kind of intuitively what these things might be. So let me give two quick examples that kind of illustrate what kind of tasks you might accomplish with these sorts of things, and then go on to define sort of from there the components of a machine learning algorithm. Again, I do want to emphasize one important point from the last slide, actually. And this point is that if we look at this notation, the machine learning algorithm is kind of the meta program that produces one of these, what I was calling on the next slide, an ML program. All right, so this ML program here maps inputs, or we would like it to produce the desired outputs for a given input. But it itself, this ML program is different from the machine learning algorithm that sort of generates that machine learning program. It can be a little bit confusing here. I think it will get much less confusing once we actually introduce a bit more notation about models and things like this. So if this is confusing for right now, just stick with it a little bit longer till we talk about some more notation. Before we do that, though, I do want to highlight a few examples. So let's talk about one example. Let's talk about the example of image classification. Let's say I have two types of images. I have images of cats and images of dogs. And I want to build a program that will tell me if I give it an image, whether this image is an image of a cat or an image of a dog. So here I would have the input, which would be in this case a picture. And I'm going to try my best to draw a picture of a cat here. Maybe in video editing, I'll add a wonderful looking cat afterwards, but something like this. So here's our lovely cat. And the desired output for this given input would be, in this case, the label cat. For a different input, say this one, that's a bad dog. Let me do a little better than that. Even I can do a better dog than that. There's our dog. Again, I'll think in post-editing, I will put a much nicer picture of a dog there. Our input is this picture, and our output would be the label dog. And of course, we would have many such examples. We wouldn't just have those two. We have many such examples. And the totality of all those examples together would give us the training set that we use to build that machine learning model, the machine learning program. But this is not the only possible example. There are many others, right? So let's take another example. This will in fact be the example that we deal with a lot in this course, which is the example of language modeling. Here, the input is the start of some sentence. So the input would be something like the sentence, the quick brown, and the desired output would be the word fox. The sentence, the quick brown fox jumped over the lazy dog, is a common sentence in the English language. It includes every letter of the alphabet. But of course, these aren't the only examples that you would have, right? The input being the start of a sentence and the desired output being the next word in that sentence or the next word in some document. Maybe you'd have another example, which is to be or not. And the next word would be to, or that would be etc. Right? And you would have a lot of these similarly. A lot of these examples, and in totality, they would make up the entirety of your training set for this particular task. Now, there is a notable difference here in kind of the quality of these two examples. So for this example, these labels, presumably the way you get those labels is you ask a person, what is this image? Is it a cat or is it a dog? Or you ask a person, what is this image? I think I drew them well enough where most of you would label them with the correct label there, maybe with some accuracy. This case, on the other hand, you actually construct the desired outputs automatically. What you do is you just collect text from some source, say the internet, and you automatically make it so that the prefix of a sentence is the input, and the next word in that sentence or the next word in a document is the output. And by the way, you could include more than just these examples. For a given sentence or a given document, you might actually have multiple such examples. So for instance, what you could do here is actually say, not only do we have the examples, the quick brown, but you would also have the quick, where the desired output would be brown. Move my Self away a bit from this. There's another important difference here. And that important difference is in this task, there is a true ground truth label for this example. We know, in fact, or we believe that there is, in fact, an actual ground truth that this image should and maybe would, in fact, be able to produce that output. In this case, especially something like this, just observe this example here. We also would believe that there's not necessarily a right answer for some of these cases, right? Many words could follow the phrase the quick. But nonetheless, the way we create examples is you just throw in every example of a sentence that has that prefix would just be tossed into your training set. And there would be a slightly different notion in this case about what we are trying to do is not just predict a single next word, but in some sense model a possible distribution of next words. But those are details that we will get to later on in this class or in the course as a whole. Okay, so with that kind of as a starting point of notation, I want to talk about the 3 ingredients of machine learning algorithms. As I said before, these 3 ingredients do allow you to specify pretty much any machine learning algorithm. And every machine learning algorithm, including, by the way, even other types of machine learning, like unsupervised machine learning, also fits in this mold, though we won't cover exactly how that works. Every machine learning algorithm is specified by 3 specific choices of different ingredients. The first of these is what's called the model. Actually, let me use bullet points. And what the model is, what models are, our models are actually exactly this, what I called before, a machine learning program. It is the thing that a machine learning algorithm produces that maps inputs to outputs. In particular, it is a function that maps inputs, so images of cats or dogs, or beginnings of a sentence or something like that, inputs to, and I'm going to be a little bit specific here, predicted outputs. And I'm going to use this phrase predicted output here very explicitly. Now, just to be a little bit more mathematical, not very mathematical to be clear, but a little bit mathematical, we can sometimes write functions like this as a function, say h. Actually, I'm going to use blue for math notation. Function h that maps inputs, so some input space, to the space of predicted outputs. That's what a model is. For example, maybe we have a function that takes as input our image of a cat. I was better at the cat, so I'll draw one of those. Some function that takes that image and outputs a prediction of what that image might be. Now, I want to be specific here is that notice that I talked about predicted output. whereas before I talked about desired outputs. So the desired output of this image is the label cat. But what we might predict from our machine learning model is not just the word cat. What we actually might predict is a kind of softer notion of how likely we think that image is to be a cat versus a dog. So maybe what you output is actually a list, and these could correspond to a list of probabilities or something like that. I don't want to be too specific here. We will get much more specific later in this course. But maybe what you actually produce from this function is a list of probabilities where the first probability always corresponds to the probability that the output is a dog, and the second one corresponds to the probability that it's a cat. So this one here is the probability that the image is a dog. And this one here is the probability that the image is a cat. And so in this case, this function kind of rightly decides that this image is more likely to be a cat than a dog. I use the word H here, by the way, kind of for historical reasons. H often meant hypothesis. Sometimes models were referred to as hypotheses. That term I won't use very much, but the notation of H at least stuck, so I tend to still use H as our function. The last thing I want to sort of capture here, and I'll do it very, very informally here, is I want to mention the notion of a model class. If we were to do our machine learning search over all possible functions, that actually is just too large a set. In order to sort of find some model that solves our desired task specified by the training data, what we want to do is we want to define some class of allowable functions. In the context of machine learning, at least of sort of modern deep learning, this is also sometimes called an architecture. And these define the allowable set of machine learning models that we can sort of do our search over. It basically is the family of models we consider. Where I will define much more what that means, and this will become much more concrete when we talk about specific classes of models, like linear models, like neural networks, etc. Neural networks, I should say, of a given size and things like that. Okay, that's the first ingredient of machine learning. The second ingredient is a loss function. And what the loss function is, it is a function that measures the difference, function that measures the difference between the predicted and the desired outputs. Difference between predicted and desired outputs. So remember, our model made some predicted output, right? It said that there was a 1% probability, or 10% probability this was a dog, a 90% probability it was a cat. What our loss function then does is it determines, essentially, if that's a good prediction or not. Is the difference between our predicted output and actual output big, or is it not very big? Right, so again, more formally, we can define this as a function L that maps from predicted inputs, predicted output, and desired outputs. 2, in this case, is going to be a positive real number. And this notation here, all it means is that it maps to a single, a real valued scalar number that with this positive sign here is positive. It has to be 0 or greater. So I should say non-negative, actually. It can be 0, but it has to be non-negative. The semantics here of the loss function is that this loss function, the value of this loss function, is large. And I'm using the quotes here on large because what large means relatively is actually not important. It doesn't matter how, or rather what large means absolutely is not important. What really matters is the relative size of losses you have on different examples in your training set. But again, it's not too important for now. The loss is large if the prediction is bad and small or 0 if the prediction is good. So one loss function, by the way, might just be to say my loss is 1 if the maximum element, the predicted output, so I take the most likely class, is equal to the desired output. I have a loss of 0 then. Sorry. If the loss is 0, if the predicted output is equal to the desired output or corresponds to the desired output, and the loss is 1 otherwise. This would be a valid loss function. It turns out we won't use that loss function. We'll actually use one more based upon probabilities, both because those are easier to optimize and because in cases like language modeling, you actually want to model probabilities, not just have a single sort of right output. And that's the semantics notation of a loss function. Finally, ingredient number 3, should have been numbering these, I guess, but maybe I'll go back and write them as ingredient number 1, ingredient number 2, and finally, ingredient number 3 is an optimization procedure. This is also sometimes called a training procedure, though training sometimes is a bit more loaded of a word. It can mean more than just the optimization itself. And so I'm going to typically refer to this as an optimization procedure. And the optimization procedure has a simple goal. Actually, I can define the goal of it very, very simply. The goal of the optimization procedure is to find the model, or really find the model, or maybe just a model within the model class that achieves low loss on the training set. That's actually all I'm going to say about optimization right now. When I say, by the way, on the training set, what I mean here is that it achieves low sum of losses on over all training examples, over all input, or rather over all predicted outputs and desired outputs on the training set. And if I want to be even a little bit more mathematical here, I can even write this as what's called an optimization problem. This I don't want to focus on too much, but because I sort of talked about inputs and outputs and a training set and predictions, etc., I'm just kind of going to kind of write what I mean by this. What we mean by this is we want to minimize, find some way of finding a low sum. If I take the sum over all inputs and desired outputs in my training set, I want something where the loss, when I take my model and predict that input and I compare it to the desired output, I want that loss to be small. I'm being very informal here. I haven't really even defined things like this notation of summation and stuff like that. This just means the sum over all examples in my training set, or all inputs and desired outputs, inputs and their corresponding desired output. But hopefully this gives you some sense of kind of the task at hand here. The training procedure or the optimization procedure is looking to find a good model within that model class, so within the class that you are searching over, that achieves low sum of losses on our training set. And that really is it. In fact, that is the entirety of every single machine learning algorithm. The only way that machine learning algorithms differ, the only way that neural networks differ from gradient boosting, differ from whatever else you may have heard, the hundreds of thousands of probably not that many, but maybe tens of thousands of machine learning algorithms that seem to be discussed and things like this, probably are hundreds of thousands at this point. The only difference between them is just their choice of the model, really the model class that you're searching over, the loss function, and the optimization procedure. I will also say that of these three things, the loss function and the optimization procedure, at least in modern AI, are basically always the same. People use what's called a cross entropy loss, and they use what's called gradient descent, or a very similar approach to gradient descent, to do the optimization. So loss function is always something called cross entropy. Optimization is always something called stochastic gradient descent. And we will cover both of those in quite a bit of detail, but not yet. What does vary a fair amount in modern architectures is the precise model class we are searching over. And this comes from different architectures you might design, different neural network architectures that you specify. This is how you get different machine learning models, basically. Of course, you can also have very different data you give the system to produce the model, but these are the two ways to sort of have different methods. But to be fair, there are now different optimization procedures as well, and different loss functions. So for example, you can think of reinforcement learning as using a slightly different loss function optimization procedure, but we'll get into that much later in the course. Okay, we're almost wrapping up now. The last thing I want to discuss before the end of this lecture is the notion of generalization. We talked about the goal of machine learning algorithm, to minimize the sum of losses between our predicted and desired outputs on the training set data. But it turns out, and I should maybe even write this, that ML, as we described it so far, ML finds a good, i.e. a model that has low losses, a good model on the training set. But this is not actually what we care about. It doesn't actually matter if we're able to find a function that performs perfectly well in the training set. In fact, it's very easy to do that. All you need to do in that case is just maintain the whole training set. When a new example, or when an example in that training set comes, you just look up in some database. So you just store all the examples in the database. When one of these examples presents itself, you just look up in that database for that input example, what's the corresponding output example? This is a simple sort of database lookup. Yes, maybe there's some sophistication. If this is an image, you have to kind of take a hash of the image or something like that, but it's really a simple problem, right? You just maintain a database, look up for that input image or input of any type, what is the corresponding output? Sometimes you can't do that because sometimes there may be more than one output, but then you just output some probability equally over both those two things. What we want is not this. We don't just want a lookup table. What we want is a model. So what we want is a model that performs well where well here just means, again, has low loss on new examples. So examples that are in some sense the same as what the system was built on. So it's still within the same task, right? So it's still, say, pictures of cats and dogs, or it's still completing sentences, not some wildly new task. But we want a model that performs well on new examples from the same task, but things that were not explicitly shown to the method when the model was trained, was optimized. And so to do this, we can't just use the performance, the loss of the model on the training set to evaluate this because, again, that could be perfect if we just use a lookup table. So to really evaluate how well machine learning models don't perform just on the data they were shown, but how well they generalize to new data, what we often use is what's called a test set. And this is an additional set of examples and so this means inputs and desired outputs that we do not use to train or to optimize the model. Then, the way we evaluate a machine learning method is we take this model we have trained from a training set and we evaluate it by evaluating its loss on the test set. And this provides an estimate of how well the model will do, not on an example that's already seen, inputs, desired outputs already seen, but on inputs and desired outputs from the same task that it has not yet seen. And in some sense, the amazing thing about machine learning is that in practice, some of the models that we use regularly, deep learning models, neural networks, all these kind of things, they generalize amazingly well. Even frankly, in certain situations where it doesn't really make sense theoretically why they should generalize well, in practice, they generalize very well. They solve the problem well. Now, I will almost end here, but I want to end with one more point before finishing this lecture. And that is that this was the complete story, I would say, of machine learning maybe 10 years ago. You had a training set, you had a test set of examples from the same task. You used the test set, trained in the training set, and evaluated in the test set. There were some subtleties, like you needed a validation set to have to help you train certain parts of your model, but this is all sort of details. That's really part of the training set in some sense. This was the basic paradigm. What's changed now with general purpose AI is that very often the loss that we use to train the model is really not that practically relevant, and it's not what we really care about in some sense. I don't know about anyone watching, but I don't personally use the cross entropy loss on some holdout data set as a way that I determine which chatbot I want to use for a given task. Right? That never would cross my mind as something to do to evaluate the quality of different models. What I do is I look to see how well do the models actually work on my task. And even though chatbots are trained for the most part on sort of the task of predicting words, I don't care how well they do at that task for most of how I use them. And so one additional element that's important for general AI models, so for some sense general AI, is that we also want to test the system on what we call downstream tasks. Downstream. Hard time spelling that. If I'm using a chatbot to solve some math problem, I probably don't really care how well it predicts losses or the loss evaluation of next word prediction. I care about how well it actually works on solving math problems. And so you want to periodically evaluate your model, and by the way, that's sort of in a very different setting because now we're actually generating longer responses from it. That winds up being what the mechanism there is you end up sampling from the predicted distributions. Again, stuff we will all cover later in this course. But point being, the training process and the evaluation process look very different there. Now, I should add that one amazing thing about large language models, and this is sort of one of some of the most surprising and fortuitous events that's happened, is that when we train them to have lower and lower loss, they wind up working better and better, just very nicely, on other downstream tasks. This is in fact why they are so useful, right? No one really cares about next word prediction. We care about using them to do things. And it turns out that models trained to minimize loss often actually do very well on downstream tasks. But it's nonetheless very important to evaluate their generalization ability to these downstream tasks rather than just evaluate them in terms of loss, even on a holdout set. Okay, so that is actually all for the lecture today. That hopefully gives you a rough understanding of the high-level machine learning paradigm. What we're going to do is we're going to take examples of desired behavior, feed that collection called the training set into a machine learning algorithm. That algorithm consists of models, or really a class of models that are allowed, a loss function and optimization procedure, and that will select a model that gets low loss on that training set. Then, after we're done training, we will evaluate the model either on held out examples of that same task or on other downstream tasks. Now, how that all happens will be the subject of the next 4 lectures or so. And we'll, after that, start talking about even more complex models that we can introduce. Next time in particular, we're going to start talking about models, and we're going to actually introduce quite a bit more formal notation in linear algebra so that we can define more formally kind of what this model is, what this mapping is from inputs to predicted outputs. So I'll see everyone next time.